Greetings to dear students. In the last video, we have seen a formula for this formula to find the residue of a function f of z at the point A if A is a simple pole. Okay, so this lemma is again a formula to find the residue of the function f of z at the point A if A is a simple pole. Okay, so second lemma, if A is a simple pole for f of z and f of z is of the form g of z by z minus a. Okay, if A is a simple pole for f of z and f of z can be written as some g of z by z minus a, where g of z is analytic at a, the function g of z should be analytic at a and g of a not equal to 0. Then residue of f of z at the point A is nothing but g of a. It's very simple formula. So very simple and easy to apply. Okay. So given that A is a simple pole for f of z and f of z is of the form some g of z by z minus a, where g of z is analytic at a and g of a not equal to 0. Since A is a simple pole, by previous lemma we have residue of f of z at the point A is equal to limit z tends to a z minus a into f of z. Here, f of z can be written as some g of z by z minus a. So, we are substituting the value of f of z here. So, z minus a will get cancelled. Then, limit z tends to a, g of z will become, when z tends to a, g of z becomes g of a. Because the function g of z is analytic at the point a. Okay. So, therefore, residue of f of z at the point a is equal to g of a. Okay, so far we have learned two formulas if A is a simple pole. The first one, if A is a simple pole, then residue of the function f of z at the point A is equal to limit z tends to a z minus a into, sorry, yes, um, if A is a simple pole for f of z, then the residue of the function f of z at the point z equal to a is limit z tends to a z minus a into f of z. And second formula is if f of z is of the form g of z by z minus a, where g of z is analytic at a and g of a not equal to 0, then residue of f of z at the point a is equal to g of a. Okay, so the third formula is, if A is a simple pole for f of z and if f of z is of the form some h of z by k of z, where h of z and k of z are analytic at A, provided h of a not equal to 0 and k of a must be 0. Okay, then residue of f of z at the point A is equal to h of a by k dash of a. Okay, here k of a should be 0 and h of a should be not equal to 0. K of a if not equal to 0 means the function is analytic at every point. If k of a equal to 0 means what will happen? The function, since it's in the denominator part, when k of a is equal to 0, the analytic fails. Okay, so these two conditions should satisfy. Then residue of f of z at the point a is equal to h of a by k dash of a. Okay. So given that A is a simple pole and f of z is of the form h of z by k of z. Since A is a simple pole, but lemma 1 we have residue of f of z at the point A is equal to limit z tends to a z minus a into f of z. In the place of f of z, we are substituting the value of h of z by k of z. Then we are separating, we are merging z minus a into k of z as one term and h of z as another term. Okay, so this will become h of z into z minus a by k of z. Given that Okay, so next, before that, we are splitting the limit for these two. So limit z tends to h of z into limit z tends to a z minus a into k of z. Okay, this is by the known theorem. Limit, we know that limit z tends to a, okay, f of z plus g of z is equal to limit z tends to a f of z plus limit z tends to. The same goes for the product. Okay, so now given that the value of k of a equal to 0, given that the value of k of a is equal to 0, so what we are doing is, here we are applying the applying the value of 0 here, because k of z can be written as k of z minus 0. So in the place 0, we are writing k of 0. I mean, instead of 0, we are writing k of 0 as k of 0 is equal to 0. Okay. So now, limit z tends to a h of z, limit z tends to a z minus, sorry, limit z tends to a z minus a into z minus a by k of z minus k of a. Okay. So this is what, since h of z is analytic, limit z tends to a, h of z becomes h of a. Okay. So this is, you have seen it somewhere. Okay, where we studied that the f is differentiable at the point a if f dash of at the point z naught, then what is the definition? Limit z tends to z naught f of z minus f of z naught divided by z minus z naught. Okay, divided by z minus z naught. Okay, so here the function is k of z. Instead of f of z, we have k of z, and k of z minus k of z, a is the denominator part, z minus a in the numerator part. Okay, so this is, which is equal to 1 by k dash of a. Okay, this is equals to 1 by k dash of a by the definition of differentiable. Okay, so it is equal to h of a into 1 by k dash of a, it is equal to h of a by k dash of a. So if the function f of z is of the form some h of z by k of z, and h of z and k of z are analytic at a, and h of a not equal to 0 and k of, sorry, h of a not equal to 0 and k of a equal to 0, then the residue of f of z at the point a is h of a by k dash of a. Okay, so this is another formula if a is a simple pole. Okay, so the next video we will see the formula for if a is a polar order greater than 1. Okay, for that we will see the formula to find the residue of the function at the point a. Okay, thank you, dear students.